All right, everybody. So this is a talk about Boost.Parser. It was recently accepted as a Boost library, and so hopefully it'll be in the next Boost release. So good news for that. And so that means this is less academic than the talk I gave last time about a library I've since abandoned. We won't talk about that. Okay. So why a parser library? Oh, am I missing focus? Why a parser library? Well, the short answer is I really like Boost.Spirit 2. And Boost.Spirit X3, I have like a minor problem with, but I also like it a lot, right? So I've been using Spirit since the beginning, and I've been using Spirit 2 since it was released as well, right? Those are both 98 libraries. So they're kind of showing their age, right? There's a lot of aspects of how those libraries work that could be done a lot better with a modern language support. X3 is that modernization, but it's missing a lot of sort of less commonly used features from Spirit X2. And it also has one particular deal breaker for me, and we're going to get into what that is in a little bit. So I really love those libraries, but I was really frustrated with them. I was writing a YAML library. YAML parsing is really thorny because the way YAML parsing works is all these different forms of the same thing. So like you'll have a list, and a list will have multiple different forms. So you might have seen in YAML files, someone will have like a vertical bar and then a new line, a bunch of vertical bars and stuff like that. Or you can actually just do explicitly JSON markup. That's another form of a list. So each of those list constructs recursively can have other objects within it. So it could have an object type, a list type, and so on. So all of the parsers beyond the lowest level parser of like, let me parse a string or a number, all of those parsers depend on each other. So you have to get everything right at the same time in order for a YAML parser to function properly. So it's a very, hey Louis, it's very difficult to get that kind of parser working, right? So in the middle of using X3 and trying to use Spirit 2, I was sufficiently frustrated with this that I wrote like a mini parser library that I used. It was only about an evening worth a week worth of evenings of effort, and that became the genesis of this library. Okay. All right. So the particular things that made me write this library, though, we're going to go into some of them. All right. So Spirit 2, first of all, suffers from long compile times. I used to be able to say that favorably compares to my library. It's no longer the case. My library is now doing so much automagical stuff at compile time. It's about the same parse time as you got with Spirit 2, unfortunately. It does have pretty nice error reporting facility, but it requires a lot of user intervention, right? So it gives you all the information you need, but you have to write a lot of code, and that code is very fiddly to make it produce good diagnostics. It also requires a lot of user intervention for the trace facility, right? So there is a trace facility. It produces a very verbose trace of every parser, every element it was trying to parse and when it was trying to parse it, and how the parse went, the attributes produced, that kind of stuff, where you are in the input. So it's very useful, but again, it requires you rather to use certain patterns in your code that you maybe wouldn't use if you weren't doing trace. So like everything has to be stream insertable, for instance, to show up in the trace. Like every attribute using anywhere in your code has to do that, or the whole trace becomes ill-formed. So there's some improvements I've made with that because I found that to be a pain point. So specific to Spirit X3, it has rules that do not compose well. And again, I'll get into exactly what I mean by that with an example later on. But the idea is that rules are the basic building block of writing complex grammars, right? So you build your rule, you test it in isolation, you put it on a shelf, and then you use it later. You want them to be able to compose in such a way that the unit tests that you wrote really do prove out that that thing works. And when you use it again, it works in a new context, and there's not a change in behavior. And then, as I said before, it's missing a few of the sort of bells and whistles from Spirit X2, some of which I really used, and in particular, I needed for a YAML parser. Okay, so both libraries also support Unicode, and the Unicode support is actually very robust. The problem is that there's a lot, again, of user intervention. It was something that was added after the fact, so you have to write a lot of code to make the Unicode support work. And it was written before ranges were a thing. So everything has to be a pair of iterators, right? You can't do iterator sentinels. You can't do, null terminated pointers, things like that. So it's not all negatives, of course. Both the libraries, they have this nice set of parsers and parser combinating operators, operator overloads that make very nice decel for the parsing space. They also have really nice semantics for how to get values out of your parse. So there's this notion of an attribute, which, like, show of hands, who has used one of the Spirit parsers before? Like almost everybody. Okay. But I'm going to give this talk regardless for, maybe video viewers or the few of you that haven't used it before, assuming you don't have any Spirit background. So an attribute is the value type that comes out of a parser when it does the parse. So if you parse a real number, you want to produce a float or a double or something like this, right? And there's really nice semantics for how you get those values out of the parse and get that result back using Spirit. And they're just fun. They're just really fun to use. Like, I don't know, the few of you who haven't used it, like the reason there was so many hands up is because they're just damn fun to use. And I didn't want to lose that in the process. Okay, so that's why this library exists. The point is to take all the great stuff that I love about Spirit and make a modern package for it. And then along the way, there's a few like niceties, things I can change about the way the libraries work, make them easier to use mostly. And so I didn't want to lose the fun. That was another important part of it, right? So I kept that same nice decel, right? The same operator overloads, most of the same parser names and so forth. All right, so now we're going to take kind of a broad view of what's in the library, the big moving parts of the library, and then we'll talk about each of those in its own section. So here is a complete parser written using Boost.Parser, okay? So this is all jammed together vertically. Sorry about that. It's the only way I could fit it on the slide. But let's look at the pieces. So first of all, you include the parser header, obviously. And then you've got your standard sort of main function. The next thing you see is namespace BP equals Boost.Parser, right? So that namespace alias I'm going to use over and over again. Everywhere I'm using something for Boost.Parser, it's going to be BP double colon. That's so you can tell what's in the library and what's not at a glance. And then we call parse. Okay, so this is one of the slight improvements. I've only got 4 names you use for parsing: parse, prefix, parse, and then there's a callback version of each of those. So the callback one, most people will never use. So really you just need to worry about parse and prefix parse. Spirit had a number of names that were, I think, slightly obscure. I think parse and prefix parse are nice, and I was able to get it down to just those overloads. So the first thing we give it is the range to parse. Okay, in this case, it's a reference to an array, but it could have been a pointer to char as well. That would be considered a range by the library. So the library is going to take a pointer to char and say, oh, you're giving me a null terminated string. And since it's isomorphic with a range consisting of a null terminated or a pointer and a null terminated sentinel, it just makes that for you. Okay, so you just provide a const char star there if you want to, and that just works. The next piece is the BP double % comma. Okay, and what that does is the BP double is the real number parser that produces a double as its attribute type, and the % says I'm going to take 2 parsers. The first parser, I'm going to produce an attribute that is a vector of those parsers, right? A vector of those attributes produced by that parser. So I'm going to repeat that parser over and over again, and I'm going to use the other parser, the one on the right-hand side, as the delimiter. So as long as I see one real number and then any number of comma real number, any number of that pair repeated, that's what that parser does, okay? The character literal comma is being treated as a parser. Yeah?
Question, does it expect pairs of things, or does the last comma not count? Are the commas strictly in between, or is there one? The
commas are strictly in between.
Okay.
So it is, the parser is isomorphic with double, then comma, then double, that thing 0 more times. Okay. And the comma there is a character literal. You could have put a string literal there. Anytime you have one of the operator overloads and you have a legit parser on one side, the other side could be a string or a character literal, and it says, oh, I get what you mean. You mean the lit parser of that literal, okay? We'll get into what a lit parser is, but basically, when you use a lit parser or a literal character or string, you're saying there's going to be markup at this place, but I don't care about an attribute for that. So it's going to consume that input and it's going to match that thing, but it doesn't produce any results. So this whole little expression produces a sequence of doubles, and it's going to parse comma delimited doubles for you. And then the next element is the white space parser, and that we're using as a skipper. What a skipper does is it lets you basically ignore anything that matches the skipper in between the tokens that you're specifying in the other parts of the parse. So in this case, we have a bunch of real numbers and a bunch of commas, and I can have any amount of white space in between those. That includes new lines, tabs, line breaks of all varieties, whatever, right? Any kind of white space and any amount. So that is how you're going to see all of the calls to parse work. You don't have to have a skipper. That is optional. Sometimes you want to parse where you don't use a skipper because let's say you want to remember the location of all the white space and commas. I mean, not commas, comments, if that's what you're parsing in your skipper. You might want to have that be part of your parse, and so you don't want a skipper. But typically, this is the way you're going to use parse. So when you call parse, you get this result. Okay, the result is something that is contextually convertible to bool. Okay, that you see on the next line, we're testing the result. And if result is truthy, then we know that inside of it, there's this sequence of doubles that we produced. Okay, so if that looks like an optional, that's because that's an optional. So the call to parse, when you get an attribute out, it's going to give you an optional with that attribute in it. So you ask first, was the parse successful, by asking if the optional is engaged, and if it was, then you have the value inside. Yeah.
Why not an expected?
I don't know. I mean, because it's not necessarily an error case to fail to parse. So basically, we're saying like, yeah, the parse didn't work, and if it did, here's the result.
Right.
Yeah.
This is one of my pet peeves with all of the libraries. It's like getting diagnostics out is super hard.
You're going to see very nice diagnostics you're going to be excited about in a minute. Yeah, go ahead.
If it's an optional result, what happened to the leftover string that wasn't parsed, if any?
What happened to the leftover string that wasn't parsed? I don't know what you mean by that.
In this case, you're expecting to parse the entirety of v1. What if you're doing parse a bit, then parse a bit more?
Right.
There's some leftover string that you didn't parse yet.
So this parse is parse the whole of the input range.
Right.
Prefix parse says I need to match, but then I can have stuff at the end. That's fine.
So the result of prefix parse includes the leftover range.
That's right. Okay. Yeah, and there's two overloads. So if you pass the whole range there, then it's just going to parse the part of the range. It's not going to tell you where it stopped because it doesn't have a way to communicate that to you. But if you give it a pair of iterators or an iterator and sentinel, it will advance. It takes the iterator by reference, and so it will advance it as far as it needs to go. So prefix parse with iterator sentinel is the way you would do a resumable parse or multiple different options of top level parse if you wanted to. Yeah. Was there a hand?
No, it's about that.
Okay.
Whether the pointer will move or not.
Right. In this case, only because the range, it does not. Yeah.
Why doesn't it just store the rest of the range in the result?
So I could have had the result return something more complicated, but what I find is that, like from a couple of decades of using these kind of APIs, that basically this is what you want almost all the time.
Okay.
Yeah, like you do resuming parses sometimes, but generally you build that into the parser itself. The top level parse doesn't get used that way as much as you would a standard algorithm. You commonly do that with.
Yeah.
Yeah. Okay, so like I said, if you've got a truthy value, then you know that inside you've got the attribute. You can dereference the optional. You can loop over the values in the attribute. In this case, it's going to be a vector of double. And then if it was not truthy, then you print out like the parse failed. Okay, so this is a full example, and we're going to be referring back to this one repeatedly. So hopefully everybody gets this before we move on. Any more questions about it? Okay.
If it's not true and you the reference, you would have an exception or just...
It does what optional does, which I want to say is not an exception. I think it's UB. Yeah.
Good.
Yeah.
Yeah. So the white space skipper can happen in between doubles and commas.
Yeah. So it's a little mind bending when you first see it, but it's incredibly useful. And the reason it's so useful is that imagine all the places you'd have to put markup here to make this work, right?
Sure.
You'd have to say like, oh, I can have some white space in front of it, or I can have between here, or I can have after this one, and all the combinations thereof. And so the skipper, essentially the way the skipper works is there's no such thing as an atomic parse, but you can think of it as like the lowest level parse thing I'm going to do. I'm going to match one character. I'm going to match one element of input. In between each one of those operations, that is sort of the first order parser. In between each invocation of first order parser, you just say like, hey, by the way, apply the skipper now. Yeah. So this works really.
The expression template or whatever. However, you can explain how it works.
Yeah. Well, the funny thing is I didn't need expression templates here. I know I wrote an expression template library that didn't use them in this very nice place to apply them. But I found that like the compile times of Spirit 2 were largely due to the expression template, reduction kind of stuff. And I found a way to do it in a way that I didn't need that. Yeah. So, yeah.
So the second parameter of the parse call, what type does it evaluate to?
The second, you're talking about the else case?
Column.
You're not talking about the else case. You're talking about, sorry?
Yeah. Parse call.
And
the
the
type
parse
of
call? Yeah. What about the parse call? I'm not following.
What is the type for the second parameter? What is the value?
Oh, this parameter here.
Yeah.
So it's some ugly, complicated type you don't want to look at, right? So essentially, the type of this is something called real parser, float parser, sorry. Float parser with some template parameters, okay? One of the template parameters is this thing returns a double. This is an object, an inline const export object that is that type. And then when you do this, what it does is it makes a repeat parser that uses this parser and the parser that you make a literal parser out of this character from. So it's a repeat parser that, I'm sorry, it's actually a sequence parser where you do the double and then you do the repetition of that pair of like comma then double, right? So there's lots of things like that in the library where you write something and lexically it looks a certain way, but then under the covers I just say, well, that's equivalent to this other chain of parsers and I'm just going to make that instead. That's part of the reason I didn't need expression templates. I found all the places I needed to do that and just did it directly. Okay, so parsers themselves can, or the set of parsers consists of these things, right? So there's first order parsers. So we just saw double, that's a first order parser. Int is another one. There's all the usual numeric types you would expect.
They have some way of saying don't eat white space in the middle of them.
Yes, we'll get to that too.
Okay,
yeah. So you've also got operator overloads, right? So we just saw the %, which is a special form of repeat. We've also got Kleine star. We've got the EBNF plus, right? Which is the one or more version of Kleine star. And then you've got the second order parsers and directives. So directives essentially affect the way the given parser operates. So you say directive name, brackets, P, where P is your parser, and it changes the properties of P in some way, right? Still parses the same, it eats the same amount of input, but usually it changes the attribute type or something else like this. This example with if, this is essentially a way of gating the use of this parser based on some condition. And the condition is truly arbitrary. You can put whatever you want here. So at this point in the parse where I write this, at this point in the parse, we evaluate this condition. If the condition is truthy, then we go ahead and do this parse. Otherwise, this whole parser fails. And then you probably have an alternative and you go try the next alternative, right? Okay. And then you have these things called semantic actions. Lots of frameworks for parsing or lexing have some sort of semantic action support where you directly associate a part of the parse or part of the lex with a bit of code. There's direct support for that as well. And then there's these things called rules, which I mentioned at the top. So a rule is if a parser is a line of code, a rule is a function, right? So it's the way you decompose your parse into pieces and units of work that you can sort of test in isolation. Did you have a question?
Was if in Spirit as well?
Yeah, if was in Spirit, yeah. Okay. So if you use any of those things like a directive or a second order parser, like I showed you the if and I referred to the whole if expression as being a parser, that's because this is a combinator library. All of the combining operations produce a new parser. You got a parser 1, parser 2, you glue them together with some combining operation. Now you've got a new parser that includes those two parsers as subparsers. That's another term you're going to hear me use. When I say subparser, I mean you've got a top level parser and underneath it it's using one or more other parsers to do its work. Those are its subparsers. Here we go. Okay, so another example is the right shift operator glues together two parsers and makes them a sequence parser. Okay, so if the first part succeeds, then we parse the second part. If it fails, then we fail the whole thing. If this second one fails, then we also fail the whole thing. What this is going to produce as an attribute is going to be, I guess we're not going to talk about that quite yet. We'll get into that in a minute. But the idea is this is a parser, and this whole thing is a parser. These two are subparsers of the whole parse expression. Okay. Did you know? Okay. All right. And all of the parsers have the parser overloads defined on them, right? So the the shift operator, like I could put another shift after this and glue another thing on the end. It would make a sequence parser with 3 things in it instead of 2. Okay. So anytime you make a new parser, not to get into the weeds, but like I've got all these like actual parsers that do the work of parsing. And then I've got this sort of wrapper type that has all the operator overloads on it. And the wrapper just has one parser in it. And so it gives the interface of the parsing. So whenever you glue together 2 things, you glue together these wrapped types, you unwrap the parsers out of them, you put them together and make a new thing. That new thing goes in a new wrapper. So you've always got all the operator overloads, but you don't have to define it for every single type all over the place, okay? And most of these parsers are pretty small. None of them allocates unless you explicitly give it, like there's one parser that's that attribute parser. It just produces produces an attribute value. It doesn't consume any input. If that thing needs to make a copy of some big allocating data structure, that's going to do that. But most of them do not even allocate, right? And so most of them are actually represented, like you can make all your parsers and most of them are going to be const expr friendly. You can make your parsers const expr and then at runtime you use them. So if I give you a parser that parses a certain string, if you give it a string literal, it's going to take the begin and end of that string literal. It's going to keep that subrange inside of it. If you give it an R value, that'll be ill-formed. You're not allowed to do that. So it's doing a lot of things like that to basically reduce the size of parsers. And the reason that's necessary is because ultimately the parser that you pass into the top level parse call is going to be some ugly thing which has a million subparsers nested within it. It's this giant type. And if all of those subtypes weren't tiny, you would have some real performance problems in some cases when you need to pass one of these things. Yeah.
Sorry, are you saying that constructing the parser does not allocate or using the parser to parse does not allocate?
Constructing it does not allocate.
Oh, okay.
So it doesn't allocate, like if you make a copy of it, it doesn't allocate, that sort of thing. During the parse, obviously if I'm making a vector of doubles, that requires allocation. So there's some attribute types that are going to allocate. But interestingly, the only time that you need to use the allocation that the library does is for things like that. And you can actually turn off the generation of attributes in places where you don't want that and do your own allocation, your own data structure that's not a vector, that sort of thing.
So allocation or not depends on the actions associated with the attribute.
It depends on a combination of the semantic actions and the production of attributes. But you have control over both of those
Right.
things.
So
yes.
you might have actions that don't allocate and the library will never allocate anything.
That's right.
If your actions don't allocate, never allocate.
That's right. If you make a bunch of semantic actions that don't allocate, that's true. Is the room mic'd? Do I need to repeat the questions? I don't know how we set it up this time.
No, you're fine.
Okay. All right.
It's right there. The stork.
That giant thing right in my face. Yeah, thank you for pointing that out. Right. Yeah, and like I said, a lot of them are monostates even, right? So like, the simpler parsers, there's no state to them, right? And so this is where we start to get into some implementation details that are kind of important. So this might sound like an unimportant detail, but each of the parsers, remember I told you there's a sort of wrapper parser interface and there's individual parsers. Well, the individual parsers each have a call overload, right? It's not technically invocable. It's not a call operator overload. But it is invocable with the call, right? The first version of call produces an attribute, and the second one lets you fill in the attribute as an out argument that it takes by reference. That's not just because people like those two calling conventions. There's a specific difference in semantics between those two that we're going to get into. Okay, so this is what I was about to say before when I was talking about attribute types. So we have an attribute type with every parser, right? So as we saw before, this thing called double naturally produces a double. This thing called int naturally produces an int. That makes sense. If you glue these things together, we have an int followed by a double. So naturally we have a tuple of int and double. Okay, now I put BP tuple rather here. By default, that's std tuple. But I have support for HANA tuples because it's so much nicer to work with. During the Boost review, actually, everybody was very against having the HANA tuple in there. They were like, "We have std tuple. Why do this?" And I was like, "I don't think you properly estimate the utility of the HANA algorithms and that nice index operator on the end of HANA tuples. Those two things are real benefits of using HANA that are really concrete. And so I have, it's an optional macro you have to define. In all my code, I have it turned on. So I recommend you use HANA tuples, but it's off by default because of the results of the Boost review. Okay. You can also have a parser with no attribute associated with it, right? So like that attr parser that I mentioned before that just has an attribute, doesn't consume any input. There's no attribute associated with that except for the one you give it. And epsilon is the moral equivalent of that with no attribute at all. It's the epsilon from the parsing literature, right? It doesn't consume any input. It always passes, or it always succeeds, rather. It matches the parse. It has no attribute associated with it, right? And there's several other cases where you have no attribute. So instead of making the attribute type void, I have this like regular void replacement called none, and we just produce that, right? And that's at the top level.
It's the moral equivalent of an empty tuple, not of an empty variant. It's a top. It's the top type, not the bottom. That's correct.
Yes.
And it wouldn't have been void.
Yeah, that's right. Yeah, and in this case, it's not even the moral equivalent of an empty tuple. It's just like an empty struct. It's like a monostate, right? Yeah. I mean, those are.
But that's what that is. It's the. It's not the initial object. It's the terminal object. But
Yeah. Yeah. Okay. So as we saw in that first example, you make your parser and then you pass it to parse, right? So in this, we have the example that I just showed previously. We have an int followed by a double. We're going to call that parser. If I pass it the input of an actual, integer number and then a real number, we're going to parse that with that parser using the same skipper from before. That conveniently means I don't have to deal with this white space right here. But I actually, in this case, I actually need that white space because otherwise that would get glued together and that would just be one number, right? So the result that returns, as you can see with the static assert, is in fact an optional tuple event double, right? So just like before, we parsed a sequence of doubles. We got back an optional vector of doubles. Now we parse an int followed by a double. That gives us a tuple event in double. We get an optional of that. Does all make sense? Okay, so we can assert that the result is truthy because in fact that is an int and that is a double, and then we can look inside and we see that this is the actual value we got out. Okay.
So without the white space, the skipper won't that fail for reading just the integer?
Yeah, if you didn't have this, then it would parse this successfully, and then it would look here and it would say, this is not a real number, and it would fail. That's right.
Could you assign that to a const per auto result?
Could you assign that to a const per auto result? Maybe. I think in this case you can. In the general case you cannot, but I think in this case you might be able to. I believe, so parses const per. All the pieces here are const per, including, nope, I take that back. I think the call functions I referred to before, I think those are not const per. I think you can basically only build parsers as const per. I don't think you can ever use them as const per. I think that there were, I tried to do that because I would really like to have this be like a compile time usable facility, but there were limitations that I ran into that elude me right now. That was pretty early on, so I don't remember the details. So, yeah.
Just to make sure, so it would start with 42 with the int parser.
Mm-hmm.
Successfully will parse it, then consume the white space with the second parser, and then we'll fail on the int parser and we'll proceed with the double parser. Is that correct?
No.
No?
So I think the question before was like, without the skipper, where would it fail? So the int parser would successfully parse 42, and it would stop because it ran out of digits. Mm-hmm. But then the next input for the double parser to consume would be the space, and it would immediately fail because that's not a valid starting character for a real number. Does that make sense? Yeah.
So it checks the skipper between every subparser.
Exactly, and it's not just every subparser at the top level. It's recursively all the way down. So essentially, like if this was something much more complicated, like not even that much more complicated. So let's say I parenthesize that and I put a star in front of it. So that's 0 or more instances of this, and I was parsing that. The skipper wouldn't just skip between int double pairs. It would skip between int double pairs and between the int and the double itself inside there, right? So essentially at every level, it's trying to skip greedily all the, places where there might be skippable stuff. So in between all of the parsers that get evaluated, it does that. Okay. So instead of returning remember I said none is the thing we return from something that has no attribute, right? This is a special, I don't have an attribute type. We don't produce an optional none as a return type. Parse is instead going to say, well, this is a degenerate optional, right? Because an optional of a monostate, that's just a bool. I'm just going to return a bool, okay? And this is the first of many sort of collapsing of degeneracies that I do. And again, having worked with Spirit for a long time, I think this is the right way to do this. If you write generic code, you really want to do things like, oh, I produce a tuple. If it's empty, it's empty. If it's one thing, it's one thing, right? It turns out, though, that where you're getting these values out is from the top level parse, and you're almost immediately using it in real code that's like not that generic and doesn't want to do things like loop over all the values of a tuple that might get returned. And the reason it doesn't want to do that is you wrote a concrete like parser there. You didn't write a generic function that like makes up some parser, then does parse, and then like does some generic thing over the result. That kind of code is, you can do that, but it's just not a common use case that people do, right? So making it fully generic and making it fully regular and not doing these kinds of collapse of degeneracies is just not a thing that usually we care about. So this is the other API that I was mentioning, right? So there's this other way of getting the attribute out, which is you pass in an out argument. And in this case, it's the same code we had before, except instead of having the result in the return value, now we just have a Boolean return value. We fill in this reference, okay? Otherwise, the code is exactly the same. The truthiness is the same. The comparison down here is the same. We didn't do a dereference because the result is no longer an optional, but otherwise it's the same, okay? Now,
do you have a type trait for that?
Do you have a type trait for what?
For tuple in double in this case, like type trait for the result type of a parser.
Yeah. So it's thorny because the lowest level character parser is polymorphic, depending on what your input type is. So you have to tell it like what your input iterator is, and then you give it the parser, but then it can tell you like what the attribute type is going to be. Yeah. So Nathan, you have a comment?
Oh, he's just saying this looks kind of retro, and there's probably a reason, right?
Yeah, so that's exactly what I was going to say is like, why would you do this old way of doing things, right? And like, I would much rather have things that are pure functions of return a value. That's much nicer to reason about. It's better for the optimizer to reason about. So there's a reason why we're doing things this way. And the reason is that so before I get to that, actually, this is the thing I was alluding to with the previous call operator thing, right? So like the reason we have those two forms is that we have those two forms of the top level parse. So we need to be able to either just give out the result or fill in the result, okay? And I think the next one is talking about why. No, it's still not talking about why.
Users don't write code to call that call overload, right? That's something that's done internally.
That's right. That's done inside the library. That's right. Yeah. So this is a simplified version of the actual int parser inside the library, right? So you give it a template parameter t, and that tells you what kind of int it is, like a long, an int, a short, what have you. So the first overload takes your iterator and sentinel, and then some other stuff. Like I said, this simplified version, and then it knows what the return type is. It's supposed to generate a t because you told it what type of attribute it is at the top. So it has a t in scope. It passes that t to this other thing that fills in the t, and then it returns the t, okay? This down here does all the interesting parsing work. And it takes an attribute as a template parameter, and it doesn't know what this type is. It just knows that like I need to be able to fill this in at some point in the body down here. Now, this means that I was able to write, for most parsers, something like this, where the one that returns an attribute as an as a result type, as a return type, just uses the other overload. So it's not a lot of extra work to have both of these. But the reason we need both of these will come up in a minute. Yeah.
Yeah. Did you really make the second call a member?
Yeah. They're both members. Yeah.
Because you're stamping out too many bodies. Like
stamping
you're
out too many bodies.
One out per t, but they're identical, right? If you already have the attribute, then you don't need the t in the second overload.
I don't have t in the second overload.
It's inside the int parser, so you do.
It's inside the int
Yeah,
parser.
it's,
What do you mean?
it's scoped inside this int parser struct, right? So that call is implicitly scoped to have a T.
Yeah, but the point is you can pass in other things. That's the reason this overload exists.
Yes, and what I'm telling you is if you made it a free function, you would have fewer template instantiations.
Yeah, sure.
Yeah.
Okay. So I guess I should talk a little bit about this. I thought I had a slide particularly for this, but I guess I don't. So the idea here, the reason we have that other overload, the one that fills in and out parameters, you're allowed to pass in other things, as I just mentioned. So in particular, in this case, I could have an int parser that actually produces ints, but then I could just give it a float or a double or anything that's implicitly convertible from an int, and it would just work. Okay, so that's why that thing exists. And we're going to get into some examples for why that fuzziness exists and that kind of opportune matching is attractive. And there's some really, really nice use cases for it. One of the things that allows you to do is you basically write all your parsers. And then let's say, the default attribute type. For the initial parser example we saw, we had a vector of doubles as the attribute type. If instead I wanted to throw that stuff into a set of int, I could just give it a set of int and that would just work. Like at the top level parse, instead of giving it the out parameter as a vector of double, I give it a set of int. It knows how to append into a sequence container that has the iterator comma value insert overload. If it can do that, it'll just do it, right? And so you would have taken your parser and said, oh, I actually realize I want this other value type out of it. And then you don't have to rewrite your parsing code. You just use it with the other value type. Or it might be that, in fact, you want to use it in two places in the code with these different value types. And you plug in the right one at the right point. Yeah.
Do you have any constraints on the attribute template parameter just to make sure that it is actually assignable from int?
No, and the reason I don't is that it's really gnarly to write that. So what you end up having is somewhere down in the bowels of like this deeply recursive like filling in of values, you get a place where these two values don't work together. One is not assignable from the other one, and you get a very nasty error message. So I would like a better story for this, but I don't have one.
Do you call some adapter in that case, which you can write in case my container doesn't allow the assignment from your library?
No. There's no explicit adaptation you would write at the API level for calling parse, where you could just pass in a new thing. But if you went into the parser itself and just put a different semantic action on it, you can make it produce whatever things as a result of the individual elements of the parse. Yeah. So that's often how you do that. We're actually going to see an example of that later. Yeah. Okay. So let's talk about attribute generation. So I've mentioned a couple of examples, right? The sequence of doubles, the int followed by double, right? So before we get too much into this, we need to talk about the kinds of parsers that exist so we can talk about like how you kind of glue them together. So this is a non-exhaustive list of the sort of first order parsers. This is just the kind of popular ones. Okay, so first you have like the white space and like kind of the special character parsers, right? So you have epsilon, eps, which like I said before, always matches and doesn't consume any input. EOI is end of input, EOL is end of line, and you've got WS for white space and blank. Okay, so the last two actually produce the white space character that they matched. The other ones just don't have an attribute at all. Okay, and epsilon is interesting because you can add the condition to it. This is actually how if is implemented. If is isomorphic with epsilon condition, where if is the condition is the condition you gave to the if, followed by the parser p that you gave to the if. Okay, so that's the thing we saw before. You would just rewrite that in terms of this, right? So what this does is, again, it says, I always match here, but if the condition is false, suddenly I don't. Okay, so that's just a way of gating anything that comes after this on the truthiness of this condition.
How does white space and blank differ?
White space and blank, blank is only horizontal white space. White space is new lines and stuff too. Yeah. Yeah, okay. There's also character parsers. So we have special character classes like control, digit, etc. We have individual characters. So char is the sort of basic character parser. Like char by itself matches literally anything except for end of input. And so this is matching a particular char. So it's still going to produce an attribute, but it has to be this exact letter. right? So if you parse exactly an A, then this will match and it'll produce that A as an attribute. This parses anything in the lowercase ASCII alphabet inclusive. So this is not the half open range, it's a closed range. And this is also same thing where you can just put arbitrary stuff in a string. Okay, so they each produce the exact matched character. Like I said before, this is a polymorphic attribute type. So if you're parsing char inputs, the attribute type of this thing is a char. If you're passing UTF-32 inputs, the attribute of this thing is a char32t. There's only those two cases inside the parser. We're going to get in, we talk about Unicode support, we're going to talk about why this is the right choice, but you either parse chars or you parse UTF-32 in the form of char32t, that's it, okay? All right, and then there's the string parser, which produces a stood string and it matches the exact string that you give it. So this is different from, like, there's also a literal parser, you would say lit of quote foo, and that would match foo, but it would not produce an attribute, okay? And so that's the literal version of the string parser, like I was just, or the string literal, like I was just saying, and then there's also the literal version of a single character. If you use them with operator overloads, you can just write the literal character of the little string like we saw before. Okay. And then there's parsers for all the kind of numeric types. I kept the same names from Spirit, even though some of them like, well, so double and int, obviously you need a trailing underscore to disambiguate them from the reserved word. Uint, you don't need it, but it has one anyway. It's just there because it was there in Spirit too, and I wanted it to be very familiar for people, and it's just a convention, right? So some people are a little bit salty about that in the review, but that's the way it is. Interestingly, with these, and especially this is handy with uint, you can specify the exact number of digits that you expect, right? So it's not just parsing any old thing, it's parsing exactly like 4 hex digits is a really common thing to do. And that's handy for like doing like Unicode escapes and things. There's also a symbol table parser, and the way that one works is you give it an attribute type, okay, and then you give it a bunch of inputs, and inputs are pairs of string and attribute, right? So if your attribute type is int, you would give it like string 3, string 4, string 5, whatever those strings are. So whenever it parses the first string, it produces a 3. It parses the second string, it produces a 4, and so on, okay? You can add things to the symbol table during the parse. You can add in 2 ways. One way is you can add it where it only persists in the symbol table during this parse. The other one is you add it to the symbol table, but it only persists for the next time you call parse with the symbol table, and then you can combine those two, right? So those are orthogonal additions, yeah.
I'm curious whether you implemented these parsers especially, or you use more fundamental parsers like, I don't know, instead of double, you do digits. And then or lit to dot.
Well, so for the character parser, it's simply equality comparison, right? You have a character or a list of characters to compare some particular character to. You just compare that one character to those. With the symbol table, it's implemented with a try, right? So it's a completely different implementation than everything else. But all of these we've seen, all these first order parsers, they each have their own particular implementation. And so, for instance, the one for real number parsing and int parsing, I'm actually using Boost.Charconv if you have it. So if I can see the header, I'll use it. And that is basically like from chars and to chars, but even faster. And that is slightly better than the Spirit X3 parser, which is what I use in a failover if you don't have Boost.Charconv. And if you don't have that, then I think... oh, no, I have that like cut and pasted into my code. So that's why I use that as the backup. Yeah.
Do they take base arguments, those parsers?
Yes, those arguments, they all have base arguments. Yeah, so you can do base 2, base 16, base 5, whatever you want to do. Okay, so let's talk about the operator overloads we have. Okay, so the first one is one we've already seen. This is the sequence of 2 parsers. So this produces A followed by B. Obviously, if you fail either one of these, then you fail the whole parse. This is a really important case. So if you have just a single right angle bracket instead of 2, then suddenly this is still a sequence parser, but suddenly like this is not allowed to fail. The B is not allowed to fail the parse. As soon as I parse A successfully, if I try B and I've got a single one of these greater thans instead of 2, then this is a hard error and fails the whole parse. Okay, and we're going to get into why that's so important. This produces a tuple of values in either one of those cases. This creates what's called an expectation point. And expectation points are really vital for producing good diagnostics. We also have an alternative parser. So A or B is the way you read that. And that produces a variant naturally of the two attribute types for A and B. Double or B, the logical or, is used for permutation. So this also produces a tuple. So this is just like the layout of this tuple. It's got an the attribute type of A followed by attribute type of B. Those are in a tuple. We don't care about the order though, right? So we'll try to parse A. If that doesn't work, we'll try to parse B. Whichever one of those works, we're going to try to parse the other one. Okay, so these can be swizzled around in whatever order you want. And you can have a chain of 18 of them if you want to. So the point is, when you want to parse a bunch of different things, you don't care about the order.
But the tuple comes out in the A/B types.
Exactly. The tuple elements are in lexical the lexical order that you see the parsers in. That's right.
Okay.
Yeah.
If you have a permutation and both of the subparsers produce the same attribute, is there any way to tell which one populated which element?
So you're saying if these both produce ints,
Yeah.
then you're going to get a tuple of two ints, and the first one's going to be the one for A, and the second one's going to be the one for B. It doesn't matter what order they occurred in, but the B one always goes in the second position. The A one always goes in the first position.
Oh, okay.
Yeah, it's for exactly that kind of thing. It just makes it really easy for you to figure out which one goes with which. Yeah.
So you lose information of the order that it was provided.
You do lose that information order, yeah.
If you want to keep that, you have to write the more complicated.
Exactly.
With,
Yeah, you would basically write out the permutations or something. Yeah.
I think X3 didn't have that, right?
Oh no, it did. This
Did?
is from Spirit 2, I believe. Yeah.
Yes, Spirit 2 had it, but
X3 might have dropped it. You might be right about that. Yeah, I don't remember.
think compilation times or something.
Yeah, I found a way to do this really simply.
Okay.
Once I did it, I was really surprised. It was like one of the simplest parsers, and it seems like it should be really complicated, but it's not. For what that's worth. Okay, so claim a star we've talked about before. That's 0 or more A's, and that produces a vector of the attribute type of A. This is 1 or more A's, and naturally it produces a vector of the attribute type of A as well. Okay, so we also have this -A syntax, which means this is an optional A. So that's equivalent to A or epsilon, right? And so naturally, because you might have A or you might have nothing, that's an optional of the attribute type of A. We've already seen this one. This is B delimited A's, right? So as long as I have one A followed by any number of B, A pairs, that's what I get for that. But of course, the attribute type of B is ignored because it's just considered to be a markup. It's considered to be a separator. So again, we get a vector of attributes of A. This is an assertion that this is true at this point in the parse. It doesn't consume any input. It just says, yes, that parse works right here, and that gates anything that comes after that in the parse. So there's no attribute for that. And this is the negative version of the assertion. So it does exactly the opposite. Like that needs to not exist, or that needs to not match that point of the input in order to proceed past that into the rest of the parse. So we have A minus B, which essentially is equivalent to not B followed by A. So the way to think of this is I want to parse an A here, but not if it starts with B. Does that make sense? So a really common use for this is like if you're writing a string parser, you're going to have like open quote, some characters, close quote. But the characters in the middle had better not be quote, otherwise you don't know where to stop, right? So you do close quote and you do char minus quote, followed by the close quote.
Is this kind of like look behind?
It's a negative look ahead. It's like right where I'm at right now, it can't match this thing. Then go ahead and do the real parse that I care about. Yeah.
I have a question.
Yeah.
That first optional, is that different from a failure in the parse, or is the same optional that you get? So
actually, all right. If you passed in this at P04, if you pass that in as your top level parser,
yes,
the result type would be, let's say this was int, the int parser. The result type would be optional of optional of int.
Optional of optional.
Yeah,
Okay.
because that inner optional actually has important informational payload.
So you will know whether it failed or not.
Exactly.
Because of parsing or because it wasn't there.
Yeah. So that would, because if that was unengaged, the inner one was unengaged, you would say that if the outer one is engaged, then that parse succeeded, but the thing that it succeeded in parsing was nothing, right? Okay. So as I alluded to before, we do collapse these degenerate cases, right? So if I have a bunch of things that produce no attribute and a claim a star expression, then that doesn't produce a vector of none, it just produces a none. You do lose information there, like you lost how many times it matched, right? That may be important to you. But the thing is that like it just doesn't come up in practice, right? That loss of information isn't really valuable. What you really want there is I have a thing that doesn't contribute to my attributes, and so I don't want to pollute the attribute space with like this number that tells me I matched a thing that I don't care about a bunch of times, right? None does not appear in a tuple, so you have a tuple of t and none, that just becomes a tuple of t. A tuple of t just becomes a t because again, a degenerate tuple is not useful, and an empty tuple just becomes a none. Okay. And the reason for the tuple of t and the empty tuple is there's some rules, especially with sequence parsers, for how the attributes get combined. So if you have a sequence parser that's like an int followed by an epsilon, then the attribute type of that whole thing is just int. And it's the whole thing is just int because first you had int none, and you say, well, I don't want to put a none in there, so let me just make it just vector of, a tuple of int. And then once you've got tuple of int, that's just int. Okay, so these collapsing rules are important mostly in that case. All right, so quick examples. So the first one we've seen a bunch of times already. The int parser produces an int. That's very, very expected. The int parser followed by epsilon that I just mentioned a second ago, that also produces an int. Okay, for the same reason. Like the way to think of this is anytime I see something that doesn't contribute an attribute, I want to essentially ignore it as if it wasn't there. It's important for the parse, but in terms of the nature of the attribute, it's like it doesn't exist. So that's why that collapsing rule exists.
Do you collapse variant as well?
Yeah, degenerate variant that's just one thing would be just the type and not a variant of that type. Mm-hmm. But that turns out not to happen because generally for a variant to essentially you're either going to have a variant of t and none, or you're going to have a variant of t and u. Pretty much all the time. Like anything you can write with a bar in between there, either produce an attribute or it doesn't. If it produces an attribute on both sides, then you end up with a variant of t and u. And then if it has a non-attribute on one of the sides, then you end up with an optional t instead of a variant t. Does that make sense?
Well, but in generic code, you can end up with int underscore vertical line int underscore.
Sure.
That would be a variant of int is converted to an int or not?
Yeah. So if you wrote that, I do believe we collapsed that down, and that's just an int. Yeah. Yeah.
Makes sense.
Okay. So we've also seen the example of an int and a double that produces a tuple of int and double. And then if you have the alternative case of int and double that produces a variant of int and double. And like I just said a second ago, if you have int and epsilon or any t and none as your attribute type, you end up with an optional of that t. So this is where it gets a little interesting. So we already talked about how one or more ints, that's naturally going to produce a double. I mean, sorry, that's actually going to produce obviously you want a double from that, right? So that's going to produce a vector of int. Interestingly, if you have just a one-off integer value at the end of that as part of the same sequence, we're just going to glom that together. This is a convention that comes from Spirit, and it's surprising how often this is what you meant. So this is the default way it works. There's a little bit of markup you can add to not make it do that. You can actually get out a tuple of vector int and int with like a little bit of markup, and you can explicitly opt out of that. Yeah.
So are you saying that plus pp int is not greedy? Like I don't get how it would ever parse.
Yeah, so I should have written the int first. Sorry, yeah, you're right. It is greedy. This is like a bogus like parser that wouldn't work for you. Yeah, okay. Fair enough. So pretend I wrote int first. Yeah, that's right. Yeah.
So in the return type, you lose the information that you wanted a non-empty vector in the correct.
If you lose the information that you wanted a non-empty vector, I don't know what you mean by that.
I mean, that information is not contained in the type because vector can be empty.
Well, in this case, you have an int. Again, pretending it was over here, you have either one or two ints. Well, no, you have two or more ints, right?
Yeah, that's what
two or more. Exactly, that's what I meant.
Right.
Two or more.
But because the integer happened at the front, you know that everything after the first one is the amount captured here. So you don't even lose the number that were matched by this subparser. Yeah. And so that's why, generally you don't end up writing this kind of code because the thing at the end doesn't kind of make sense. The only time this would really make sense would be you could maybe change the skipper in here to something else. And then you have white space to separate this. And so you would maybe turn off skipping, or not turn off skipping, sorry. You would turn off skipping around here and put an explicit like boundary of some kind of white space or something. So you could write this, but it would require a very different kind of shape.
Yeah, usually my question is when you generate these expressions programmatically, right? Not when you write them by hand.
Yeah.
So you have generic code, you might end up with sometimes
and
double with plus integer, plus int, or sometimes it would be int plus int. And it would be two completely different types.
It would be.
So generically, you will have to handle two cases: tuple double vector int, or vector int. So they're completely different.
I mean, I'm a big fan of degenerate programming. It just doesn't apply to parsing very often. That's the upside. Yeah.
So does this work with % also? So if I wrote like bp int lit comma like plus bp int, that would also squish them into a vector.
Absolutely. So the rule is essentially based on the attribute type, not on the particular parser. So anything that produces a vector followed by a singleton or preceded by a singleton, the singleton gets jammed together. But they have to be exactly the same type. So if I had short followed by a bunch of ints, I wouldn't be like, it's close enough and put them together. It would be a short followed by a bunch of ints. Yeah.
All right.
Yeah.
Is there a trick that you can use to get the tuple of int and vector int?
Yes. Yes. Okay. Like I said, there is some markup for that. We'll get to that. Yeah. Okay, so like I mentioned before, there's kind of these collapsing rules, especially with sequence parsers, right? So Spirit had a bunch of rules for this, and a lot of them were documented, a lot of them weren't. And so I would run into these cases where I got this attribute, I don't know why I got this attribute, and I don't know how to figure that out, and it's somewhere in the bowels of the implementation why it does that. So I wanted to have a reduced set of collapsing rules and so that I could just put them in the documentation. There's these 5 rules in this order. This is what happens. You can reason about this. You can internalize those rules and move on. So I've tried to make those a smaller set and make them easily described, right? So the thing I mentioned before about, one example is the semantic for Spirit 2 is if I have a string, right shift string, then I'm going to produce a single string out of that. I'm going to jam those two things together, right? I don't do that. I assume if you're parsing 2 strings, you treat those as 2 strings, right? And then if you want to jam those together, there's a way to do that. There's also rules for how that out argument that I referred to before, it can be fuzzily similar. It can be structurally similar. I don't mean in the sense of a structural type. I mean broadly, small s, the structure is similar enough. There's a bunch of rules for how that works, and we're going to get into some of that too. These are also explained in the online documentation, and I've also tried to keep them fairly short. These are a little bit more involved because they involve a lot of recursion. And they involve a lot of different kinds of matching that don't exist in Spirit because now we have the technology to do a lot of these matching. So for instance, if I produce a tuple and I want to match that, or I want to fill in a struct with 2 elements in the tuple and 2 elements in the struct, and I can assign across those 2 elements element-wise, we just do that. You don't have to do the Boost Fusion adapt struct macro or anything like that. It just works, right? Yeah, I've got a fan of that. Okay, so here is a little digression about how we do this out attribute matching stuff. So let's say we have an attribute. This is the generated attribute for the parser, the attribute one is. And then the out argument we give it is out, okay? So if this first expression is well formed, we stop, we're done, okay? I can just assign across there with a move, and I'm gonna do that. Otherwise, if we have attr, which is a tuple, and out is an aggregate, and it also works the other way around. And if we can map across those 2 element-wise, there's an implicit conversion for every element-wise move assignment we want to do, then we just do that. Finally, if attr is a tuple, and this is obviously pseudocode, this doesn't really work, but if I was able to write something like this where I map the individual elements of the attribute into a constructor call for out, then I'm going to construct an out from these individual elements and assign that to out. Okay.
Yes.
So it's like I used to have to write tons of semantic actions that did this stuff. Well, not this stuff, but this stuff, right? And no, in Spirit 2 and in Spirit X3, I had to do that a lot. And so now this is just automagical. This is where all the compile time slowdown came from. This is a lot, right? At compile time. I'm hoping that later versions of language support, I'm going to have metaprogramming support where I can get rid of a lot of this stuff that's just kind of brute force template, messing about. Okay. Yeah.
You're going to have to show me that code because I think I have ideas.
Well, yeah, I think I'm doing it the best way we can in 17 and 20, but maybe not. And I'm be interested to see if you have an alternative.
Extern variable templates?
Extern variable templates.
Oh, yeah. It's a pattern matching context, man. It's
Okay.
very nice. It's like it's like a third of the cost.
Really?
Yeah.
Okay. Yeah. I'm definitely interested in seeing that. Yeah. We should talk about it later. Okay. So this is why you present at this conference. So we have our out attribute. If it's some kind of container, so this is the thing I mentioned before, right? So if you have a vector of doubles and you want to parse that into a set of int, well, we can detect that the set of int is a container, right? Because we look for begin, end, and the positional insert overload. And we're like, oh yeah, it looks like a container to me. Like I can stick stuff in there at a certain position. And if that position is the end, right, I just give it end. And that's a hint in the case of sets and maps. So it's just ignored basically. It might be a slight pessimization, but in the case of a vector, it does that consistently. So we can use this API to insert into any of the standard containers that support that interface and it goes in the right place, okay? Mm-hmm. So what that means is that if I'm parsing a sequence of things and you give me a sequence container or any container that controls a range of stuff, I can probably like take the thing that I'm, iteratively matching one at a time and stick it into the output. If I have an optional of whatever the attribute type is as the out parameter, then I'm going to look through, I can see through the optionality and I'm going to say, oh, I can just stick it in there. Also, if I have, this one seems completely unreasonable, but it turns out it comes up. If I have a container inside of an optional, I look through the optional and I do what I was talking about doing the assignment across containers, okay? So this basically covers the sort of quadrant box of like, do I have a sequence of things or one thing? Do I have an optional thing or a real thing, right? And it covers all of those four cases. So once I've found that I have these things structurally like this, then I try to look at the value type of the thing that I unwrapped from the optional and or container. And if I can do that insertion, then I'll do it. And the insertion, the predicate of whether I can do that insertion is the stuff from the previous slide. Okay, so this is a recursive thing where we look through the optionality, we look through the containerness of the out parameter. And if the stuff that we're parsing can be jammed in there, we're going to do that. And part of the question of can it be jammed in there is, are we parsing a thing that we can use to construct an element of the container we're inserting into, or map a tuple to an aggregate or whatever? We're going to do all those kinds of operations. Yeah.
Yeah, going back to the example from the beginning, would you put a double into an int container and lose the information about the fractional part?
Yeah, if it's implicitly convertible, that's good enough. Yeah, and so you get truncation.
Will I get a bunch of warnings then, or
yeah, if you haven't turned on, yeah. Right. Yeah, no, I'm not doing a static cast. No, I just do an assignment.
Okay.
Yeah. No, that's true because I would be hiding the warnings from you if I did that. Yeah. I'm not doing that. Yeah.
So is there a better way, or should I abuse this to fuse a fold into the parse?
How would you use this to fuse a fold in? I don't get it yet.
Because insert is just the fold operation.
Okay.
Effectively, making a vector is folding a bunch of values into a vector.
Right.
If I wanted to add them up instead of putting them in a vector or map or whatever, I would make a struct that abuses this.
Yeah, absolutely. So if you made a thingy that had this API and then did something completely different, I would be your biggest fan. Yeah, that's great. That's awful and awesome. Awfully awesome. I don't know. It's one of those. Yeah.
So if you pass a vector and it's not large enough, it will start doing inserts at the end. Like
a vector that's not large enough. What do you mean? It's
as a no parameter. You pass a range.
It's going to do a pushback, I guess. Right?
Yeah, it's gonna it does this instead of a pushback.
But only when it doesn't have more space. When
Are you talking about when it exceeds capacity and has to reallocate?
yes.
Yeah.
No,
Sure.
when it exceeds the size.
But I mean, a vector doesn't. I mean, vector has a size, but I'm inserting, so I'm increasing the size by 1.
Yeah.
Oh, so
Yeah.
if you know that you have 10 integers, you pass a vector of 10 elements that are already there.
Then it's going to end up with 20 in it. Yeah.
Oh, okay.
Yeah.
I don't like that. As I was smarter.
So it turns out that if you're in the middle of the parse, you actually want this append behavior because usually the thing you start with is empty. And if it's not empty, it's usually because you opted into a merge strategy for combining two things that are element-wise containers. And we'll get into an example of that.
But it's not optimizing the common case in which you know how many elements you're going to parse. Sometimes you know, because you read it before, for example. Yeah. And then you make the vector with that size, and then you have it from before.
You just
capacity.
Yeah, you just do reserve in that case, and you get the optimization question is
well, but if you are reusing the same vector, you know.
Yeah, sure, but then you just clear the vector and it's still got the capacity. You reuse it. Yeah.
Well, you call it reserve anywhere. Kind of dangerous too. So.
You can clear.
Maybe
it's not dangerous.
Yeah, go ahead.
This might be a pedantic question, but do you...
This is the conference for pedantic questions.
Do you insert with stood move of X, or is it always...
Yeah, it's always going to be a move there.
It's always a move, okay.
Yeah.
Can I insert into stood array instead of a stood tuple?
No, because it's going to use this insert. It doesn't have insert.
Yeah, but when I put in a tuple from the outside, you can't insert into a tuple.
That's right. It only works with like... something with a begin and an end and an insert. Tuple doesn't have any of those.
Oh, but you'd be using the std array get interface.
Std array get.
It looks like a tuple. It barks like a tuple.
Yeah, but
std array barks like a tuple.
But I don't use that in this case. That's the case.
Not this case, but the previous.
The previous slide, yes,
yes,
absolutely, yeah.
Okay.
If that's what you meant, yes, I think that works.
If I got a homogeneous type, I could pass in an array instead of a tuple.
I think that's right.
Yeah. But you're using
and if you can assign element-wise, and that the consistent element of the array matches with all the disparate elements, I think that works. I don't have a test for that, so you don't hold me to that, but I think that works. Yeah. Okay, so this is just relisting the original example without the main and without the headers. Okay, so that's just what we've seen before. Just to refresh your memory, we're parsing a comma delimited sequence of doubles. Okay. So the out arg form, like we said, is I produce. Not produce. I fill in a vector of double right there. And then if I wanted to make that a set of double, then I could do that as well. Right? I just put that there and everything's fine. Okay. So this kind of looseness is really handy in the way that I mentioned before, where you have the same parser, you want to use it in multiple places. If you don't like this, don't ever use it, right? You don't have to use the out argument form of this. You can just get the value straight out and never have this fuzzy matching. The fuzzy matching is really useful in some context though, and that's why it exists. Did you have a question?
So instead of, let's say, set of doubles, can you pass a set of objects, types of constructible from a double?
Yes. So if I had a set of int or a set of like complex, that would also work. Yeah. Okay. Also, if we're changing the parser now, obviously, this is the int double case that we saw earlier. So if I parse int double, that produces a tuple, but if I give it this thingy to fill in, that just works. So this is one of the concrete cases why this fuzziness is so nice. Because very frequently, like, you don't want to have to write this thing, because the way of doing this that I did in Spirit 2 was like, I didn't really use the adapt struct thing. I just would write semantic actions here that filled in some temporaries, and then the temporaries would be used at the end of this full parse to make a thingy. And that would be the attribute type of this whole expression, right? This is much nicer in my opinion, much easier to do. And then taking it one step further, if we have a different thingy that is only constructible from the int and double, and again, like, I just kept it the same for slideware, but this could be a char and this could be a float or whatever, right? As long as they're compatible, this works. And I would construct from those elements in that tuple, I would construct the other thingy and fill it in. Okay? Yeah.
Would that also work if the int double was optional?
If the int double...
So if the whole parser was an optional parser?
If this whole thing was optional, yes.
You could call the...
That's right, it would.
Okay.
Yeah.
This is probably a feature request.
Okay, next question.
But it looks like you could support in place type other thingy instead.
In place type. What do you mean in place type?
In place type
In place
T on
type?
other thingy,
Uh-huh.
because that would mean that I didn't have to have that be default constructible, and that would kind of be really nice. Instead of OT being
Yeah.
other thingy, if
Okay,
it were
so-
in place type other thingy.
Yeah, so you're getting to one of the very opinionated things about the library. Everything is regular in the library. If it's not, go away. I
think
know-
that since move semantics, default construction is not part of.
Default construction doesn't belong in regular anymore.
Yeah.
I think it does, and I think the fact that we have move semantics means that you should have default construction, because the default constructed case is the same state as you would have when you move from something. So you have to reason about that extra case anyway. So essentially, the upshot is, I assume that this is regular. I assume that everything is regular. I'm constantly putting stuff on the stack as like a temporary and then filling it in and doing stuff. It's everywhere. So anything that's an attribute that you get from the outside, all your attribute types, everything you use in the library, I expect it to be regular, and that's documented in the online docs that like, hey, it's got to be regular.
Okay.
Yeah. I know it's not popular with some people, but it's popular with the right people.
Thank you. I will argue with you tomorrow.
The insert trick was in Spirit as well, or they did it
No.
different?
No, if you're talking about this kind of thing, though, this is...
for the container.
Oh, yes, for the container matching, absolutely. Yeah, so you could pass a set of int where you expected a vector event, and that would work, or vice versa.
But it will insert or will create a vector?
It would insert. That's right. Yeah. Okay, so now let's talk about semantic action. So this is how you associate with a successful parse some bit of code you want to run after the success of that parse. Okay, so we do this with a function. Usually it's a lambda, and it only gets called when the parse succeeds. So if you look at other frameworks for lexing or parsing, they have some facility for this almost always, right? So from Flex, this is actually in the Flex docs. It says whenever I parse the username token, go ahead and use this as some instrumentation, print out this thing. This is some, function that I don't know if this is a POSIX function or it's something in their code or whatever. I don't know the example, but the point is it's going to run that little bit of code whenever it does that part of the lex. Okay. Semantic actions work the same way. You do a parse and then you put bracket A for your action. And then when that parse succeeds, then you're now inside that semantic action and you can do whatever you want to do in there. That's generic code, or it's not generic, it's a freeform code, whatever you want to write in there. So like I said, you use the index operator. This thing is almost always going to be some lambda. Usually you define lambda out of line. There's this ugly thing where even if you put spaces here, putting the lambda introducer right here, like thinks it's an attribute. So you almost always define these things out of line. But it turns out that like defining them out of line isn't really onerous, because almost always you want to write the semantic actions in such a way that they're reusable in multiple places, or probably you don't need a semantic action there. That's not always the case, but that's typically the case. When you attach a semantic action, it disables the attribute for the whole parse. So this, or not whole parse, but the whole parser. So this parser might have produced a thingy from the previous slide, now produces a none for the whole parse expression, including the semantic action. Okay? All right.
Is it passed to the action?
You're asking if the attribute's passed to the action? Yes, indirectly, and we're going to see how it's passed through a thing called the context, right? So the context, almost all the semantic actions, or almost all of them are going to be a lambda that have this kind of signature, but they all have to have, I shouldn't say that. There are some places where you can write a different form of semantic action in relation to rules that's like just kind of a nicer way that makes you have to write a little bit less code. But this form always works. So the way this works is you have a deduced parameter type for this reference to a context. I give you the context object, and then you call a set of functions that are defined on to be compatible with any context object, and then you get things out of the context. One of the things you get out of the context is the attribute, for instance, right? And then I think we have a more concrete example here. Yeah, we do. Okay. So let's say we have this lambda pushback. We're going to capture this result that's in scope. Again, we have this generic context. You don't know the type of the context because the type of the context is always changing. Okay, so at different times, I'll have a parser that has a semantic action attached to it. That means that it forms a thing called an action parser. The action parser uses the parser inside of it, does the real parse. If the parse succeeds, then it invokes the semantic action. First, it loads some things into the context. Often when it loads something into the context, it is, for instance, setting a pointer to the attribute, which has a certain type that might not be the type of the attributes in the context as you received it so far. So it's going to change the type of the context. You're basically going to make a copy of the old context object with a new pointer to the new attribute, and that goes in here. So then this is one of the things that are specific to the context. There's a small API of functions you can call. This is the exact same naming convention from Spirit X3, Spirit X3. So you say attrib of context, and that gives you a reference to the attribute. Okay. If there is no attribute, it gives you a none. Okay. Because some things don't have an attribute, and sometimes you call this in a place where an attribute doesn't make sense, and it gives you a none. Any of these things that you call in the context, if it doesn't know what to do, it just gives you a none. Okay. And that becomes very important later on. All right, so what we're able to do then is just say, well, I've already captured result. Let me just push back whatever the attribute is into result. So clearly this works. Like this is truly generic, except that it captures this particular result with a particular type. The rest of it's generic. So you could even have like, a context that would get whatever container you want to insert into and some state that you've latched somewhere in the parse, and this would be fully generic, and you could just have this pushback thing. So if the context object, the attribute you get out of the context object is implicitly convertible to bool, then this just works. Okay? Yeah.
Yeah. So if the action returns a value, what happens to that value?
It returns a reference to the value. So you're able to move it or do whatever you want with it. In this case, I know it's a number, so I didn't do anything special. But
if the action,
is
a callable, returns a value, does anything happen to that, or are you throwing it away?
Remember, attribute expressions don't return an attribute ever. That's
what I'm getting at.
So there isn't one that returns a value.
I mean, an action is a callable.
Yeah.
Callables may return things.
Yeah. The thing that
if I give you a callable that returns something, what happens to the return value from that callable?
Is ignored or
pushback returns something.
Yeah.
Yes.
You're saying if this returns a value, pushback the semantic action returns a value, it just goes off into space.
Okay.
Yeah, I'm not doing anything with this except there's another form that you can use with rules that does something. Yeah, I misunderstood where you were asking for that. I thought you were talking about the parser itself. Okay. So if I apply that to the parser we had before, so instead of having an out attribute, or instead of taking the attribute out of the call to parse, instead I apply the semantic action to each individual double. Now it's going to take that captured result, it's going to fill in all the values, and then we have the rest of the code is the same, right? Does that make sense? So the semantic action now, every time it sees a double, it's going to push it back into the result. So instead of the parser as a framework that knows how to generate attributes, generating the attribute for us, we're saying, hey, don't generate an attribute from this parser. But this parser is going to give me an attribute that I'm going to stick into the result that was captured in the lambda. Okay? Yeah.
Had you considered making the return value, like if the lambda were to return a value, that would become the attribute of the resulting parser?
You're given the attribute, so there's nowhere for the attribute to go, except that there is a form that does exactly that for rules. So the rule has an attribute. It has a parser inside of it that produces an attribute. And the way you assign through is you just say like, yeah, if I have a semantic action associated with this and it returns a value, and that value is implicitly convertible to the rules attribute type, then we just do that assignment.
Okay.
Yeah.
That's what I was waiting to hear about.
Okay.
Why does this call to parse return a bool?
No, returns an optional, right? This overload.
No, this one returns a bool.
Because
what is the attribute type?
Expecting that.
What is the attribute type of this whole expression?
None.
It's none. So it returns a bool. Yeah. Does that make sense? Not really?
I thought the
So
it degenerates.
we ignore any attribute type on this side. Obviously, we care about the attribute type over here, but this expression, because of the semantic action, does not produce an attribute anymore.
Okay.
Yeah. So a repeated none is just a none.
Can you have both, like an action, but also an attribute?
I'm sorry, can you say that again?
Can you have an action and then also return something?
Can you have an action and produce an attribute from this?
Yes.
No.
One.
Not without a rule.
Yeah, you can make a rule that thing lives in, and this could be a subparser that then provides that
So
attribute
you
out
put
of the
that inside the lambda or something like that? No, you cannot even do it there.
No, well, inside the basically that's what we're doing here is inside the lambda, we're grabbing the attribute and sticking it somewhere as a side effect. Yeah.
What if a higher level rule that uses this one fails? And how does the side effect? It still happens, right?
Yeah. Okay. So what happens with side effects is if you have a parse fail, and it is something like there's certain parsers that when they fail, they basically reset the object. So if you've got a repeat parser that is a Laine star or a plus parser, if it parses a whole bunch of things and then it comes to one and it fails, then that's just the end of that thing. But if there's some kind of like there's repeat parsers that have to happen a minimum number of times and a maximum number of times. And if it fails after it's parsed 2 things, but it needs to be a minimum of 3 things, then it fails the whole repeat parser. So its attribute type is a vector of t, but because it knows it failed, it doesn't want to leave some stuff hanging around. Especially because there's alternatives, you might go back and try this thing again. You want to explicitly assign it to a default constructed vector. And so that's why regular types are so useful, because I use them to reset state in some cases like that.
Right, but for an arbitrary semantic action, right, you could...
So semantic actions, because there's arbitrary code in them, I can't see that, and so I can't reset it. So you get garbage. Okay. This is one of the reasons that you shouldn't prefer semantic actions typically. Yeah. Okay. But did you have someone had a question? No?
Actually, did that photo where a result in this very specific example, where is it? Like, where does it come from?
Come on.
One line above.
Right there.
Okay, all right.
Yeah, it just wouldn't fit on one slide. Sorry.
No, it's all good. I get it.
Yeah. Okay. So again,
should that have been an out parameter then into parse?
No, it's captured into the lambda.
Right.
Wait,
okay.
Zach, I have a question.
Yeah.
So can you still pass an out parameter into this here still or no?
You can write whatever you want, but I think it's gonna be ill-formed. I think
it needs to be convertible to empty.
I think basically like wait a minute.
No,
I think it just gets ignored basically in this case. Well, now that I think about it. Yeah.
Because the attributes is none? Yeah,
the attribute is none. And so I don't think, no, is that right? No, I think what might happen is if it's not convertible from none, then that would be ill-formed. Because somewhere in there, I'm going to say like, oh, I did the parse. Now let me fill in the out attribute. So I actually don't know. I'd have to write it. I think it's going to be ill-formed in some cases and then ignored in others. That's my expectation.
It seems a bit weird that like semantic actions, like I might use to just print stuff and want to collect the result in some structure still.
Right.
They're not semantic transformers. They're semantic actions.
Yeah. There's a transform you can do to do stuff like that. You can put your side effects in your transform. But this is specifically like I want to do something that's an important side effect. And if it doesn't participate in the parse, you probably don't want to put in a semantic action. If the side effect doesn't participate in the parse result or something.
Oh, I see.
Yeah.
So semantic actions are like it's like the expectation is that it's like a consuming action.
Yes.
For the parse.
That's right.
Yeah, it's the same.
Yeah.
I see.
It's essentially the same.
I mean,
That's right.
the flex example wasn't anything to do with the parser. It was a printf.
Yeah, that's true. Yeah.
So
that is different from the flex example for sure.
But I think that's why I got tripped up.
Okay.
Because I was thinking about the flex example where I might just want to get them diagnostics for where I'm at in the parser or whatever. But then
and so there we're going to talk about trace. And so the way to get like verbose information is not via semantic actions, but just turn on trace. Okay. Yeah. So I'm gonna try to move on. I'm trying to get to a good stopping point before the break. Okay, so like I said before, there's a completely different way of getting stuff out. You have the out argument way of doing things. You have return the value of the attribute, and now you have the side effect thing. But the thing I keep saying is don't do it this way, the semantic action way. The reason is that you have all these things of like, well, I can't see what you're doing in your semantic action. It's truly arbitrary code. The framework already exists, already has ways within it that exist to let you produce the attribute at the right place and get it out without using a semantic action. So prefer that. Sometimes you strictly need to use semantic actions, but the point is to sprinkle them very judiciously. Yeah.
Yeah. So the question is how would I record like a starting tag to match the right ending tag? without semantic action.
Yeah, so that's a great example of somewhere where you need to write a semantic action. Yeah, so if you had an open tag and a close tag, you want to put that in some scratch space, and then when you parse the close tag, make sure it matches, for sure. Yeah.
Do you have type erased parsers?
No. You'd have trouble writing them. Like, I don't think it works very well with the way I wrote the rest of the code. Yeah. Yeah.
Have you considered doing a degenerate case for a homogeneous tuple and then making the attribute a stood array?
No, I have not considered that. I mean, that's not unreasonable, but I think the fact that you expect tuple almost everywhere, that would be surprising to me.
It supports the tuple protocol. I don't think it'd be that.
Well, so let me put it this way. If you wanted to use that as an out attribute or an out argument and just make it fill that in for you, that would work, right? But in terms of, if you're talking about like making the attribute generation rules change that way, I don't think I'd be in favor of that, because I really want it to be like, it's just always a tuple. Like, I don't care what the types are. It's just a tuple of stuff. I got one of these at a time. I put them in the right slots, and then that's all the representation I need.
Yes, because we love recursive inheritance.
Yeah, right. It's my favoritist. Yeah. Okay. So where you put the action is important. So we saw before, I put the action on the double. That means that the atter of context is always going to return a reference to that particular double that I parsed. But if I put it on this whole expression that produces a vector of doubles, now the atter of context produces the vector of doubles. Okay, so the semantic action, like where it lives in the parse, tells you how much of the attribute you get. Okay, this is a good stopping point. We got 5 minutes left. The next part is going to be about rules and how they work. And I'm glad I left plenty of open space because we got lots of questions. So we'll resume this after the break.